this is a very dense region of stars. So, and
yeah, so that's why we look at the bulge, because there's just a bunch of stars there, and the probability of seeing a microlensing event in the bulge with millions and millions of stars is about 1 in 3 million. Because it depends on the orientation and just a bunch of stuff. So the more stars you have in one spot, the more likely that one's going to cross in front of the other. So it's kind of self-explanatory. So that's why they look at the bulge, because they want as much sample as possible. And so, as Kevin was mentioning, OVI is actually an automated telescope that finds varying stars in the bulge. And so it's automated. It does this over and over and over every night. And if it detects something that looks like a microlensing event, because it has very distinct behavior versus a variable star or something else like that, it contacts all the planet collaboration telescopes. And this is done over the internet. So another wonderful thing that stuff is telling us about is like while we were observing, we actually got an email and saying that we need to go to observe this object because it looks really interesting. So with the internet, it's really easy to follow up these events that happen once in a lifetime. And so basically they observe this until it's over, which basically means until it's that one event. So this is one of the objects that we looked at over the summer at the 61-inch. And as you guys can see, it actually doesn't go all the way up to 1, but you go here, this thing here, keep on going, and that was October 19th, which was a few days ago. So obviously they're still observing it, but it's only one telescope, as you can see. Because the most important part of this curve is basically the top, and then if there's any random spikes. So let's see if people are paying attention. What are the random spikes? Yeah, there you go.
You see some with more than one spike? Or are you just lucky enough to get one?
So if you actually, let's say you see one over here, but then you see one over here. So then it'd be, I don't know. I don't think they've observed anything like that.
but it's probably possible.
It's probably possible. It's probably like bigger planets make different spikes than smaller ones, and you can observe that. It's a good question, though. I don't think they've observed the spikes yet.
So the interesting thing about this plot is that you'll notice that most of the data fits along this nice curve. We have like 10 telescopes looking at this object, and some, like this one, has a really crappy curve. And I don't know why their error bars aren't larger, but some telescopes are placed in better locations than others. The major issue with us is that we're actually the furthest north for this survey. So our error would probably be due to looking through more atmosphere. But in general, I think our data fit most of the curves. So we were okay. Others, like that one in the middle, I don't know what was wrong with them.
Yeah, so we were looking in the direction of Sagittarius most of the time. And so Sagittarius doesn't get very high in the sky. And so, as I don't know, people tell you in their classes, you're supposed to always look as close up as possible. And we weren't doing that at all. Like, I think our best air mass was like 1.93 or something. So, but we were getting good science out of it. So our results. So we spent 5, 6 nights at the telescope, I don't know, something like that. Some, I think we had 3 in a row.
Yeah.
Observing all these objects, all these stars, not knowing if we found anything, until they tell us that we find something. But we actually found a lot of cool stuff. So out of all the objects that we observed, we helped discover 3 extrasolar planets and 2 brown dwarfs. So, because some nights we would actually switch objects. We would look at one object for 5 minutes, go to a different object for 5 minutes, and then do that all night. Or we would just look at the same objects the whole night. It really depends on the priority of the objects, because like some are like at the peak, so they want you to observe it as much as possible. Some are still going up, so you can observe it more like that. So, but one of these planets that we discovered is actually believed to be the first exosolar planet orbiting a brown dwarf. So,
So that's a pretty significant discovery.
Yeah. Yeah.
Wait for 3 years for that paper to be published.
So it's pretty big deal. It's actually the only method that actually can discovered something like that currently as well. So that was really cool. And like the guy who like put this out, he like sent us a crazy email. I was like, oh my god, like there's like the biggest news ever, and it was like pretty cool.
The other fun part of this project was getting to Skype some French dude who just woke up and is cursing a storm because something's not working.
Yeah.
And
So we got to Skype people all the way around the world, and that was pretty cool. And I have a quote here about when I was talking to Blythe earlier this summer, and I was like, we helped discover several exoplanets this summer. And Blythe was like, where at? And I said, in space, of course. Yeah, where do you think, Blythe? So all these things are in space. Just like you guys know. So these are pictures that I actually took throughout wonderful
Looks
summer.
like serious business, guys.
Yeah, doesn't it? See, there's actually a iridium flare taking over the world. We're watching The Matrix. I don't know if you guys can see that or not. We actually had a Matrix marathon. There's the ISS.
and a ghost of me.
And there's a ghost of Kevin.
Jake took a lot of pictures of me. It's creepy.
At least you're not on Google, Kevin.
Yeah, but very special thanks to Rob Zellum, who's a grad student over at LPL that we worked with on this.
Yeah, so one of the professor I'm working with right now, that's her grad student, and he was like, hey, you want to help us observe over the summer? And I was like, sure, why not? And so that's observed. And those were inventions. Any questions or
I
comments?
have a question.
Yeah.
I don't. This isn't late. It might have been like the first thing you talked about. So how do you go about finding? So like, okay, so you need it to be like a micro lens. How do you just go and look at various micro lens things and hope that you get a little blip by it? Or is there some kind of like systematic thing that you can?
Oh, do you mean like how do they determine if there's going to be a blip or not?
Yeah. Like where do you look and why do you look there?
Okay. So first, I'll start from. So basically, this is what it's supposed to look like if it's micro lens.
Mm-hmm.
This is without a planet, and so this is a very distinct feature. So there's an automated telescope. I don't know where that was
Oh,
at.
okay. The thing that looks like Google that's not.
Yeah, Olgi or something. I don't know where it was.
The automated thing that looks for things that look like that.
It's looking for everything. It's just looking for varying things, but specifically it wants to look for stuff like that.
Okay.
And then once it finds stuff like that, it contacts everyone who has these big telescopes or small telescopes and say, go look at this object.
And so then they just observe eventually how they get a blip.
Basically, yeah, it's all probability.
All right.
So there was probably several objects that we looked at that had nothing in it, and it just was a regular thing. But it's basically you're trying to see how often you see this blip, and that actually helps you determine how often there are planets around stars and stuff like that. So if every one of these you observe a blip, then that means exosolar planets are very common. If you don't all the time, then it means they're not as common as you think. So
I think, before we get to Brad's question, over the summer I think we looked at about 7 different objects. Of those 7, we detected planets, around 3, and then 2 brown dwarfs. So we were very lucky with the objects that we got, but some people, this is all they do for their research. So they just gather data on telescopes, and, their chances at finding things are 1 in 50.
yeah, so the grad student we're working with, Rob, he went to Tanzania to actually get trained for how to do this stuff. So he was there for 4 months, and they found 1 object. And we did this for 2 months and found 3 objects. So
But he did get to Tanzania. So.
he did go to the Tanzania, yeah. So do you had a question?
Do you have any idea what the sizes of these planets are? Are they like the massive Jupiter planets that are so common?
I do not
now?
know that currently.
I'm just wondering if, because, these are probably, if, like you said, up to 1/10 Earth mass, then they're way too small to use radial velocity to try to back up the test with.
I'm pretty sure, I think that the size of the object is related to how big this blip is. So if this were a Jupiter compared to a sun, then an Earth thing would be 1/10 that height and width. So it'd be really hard and it would be really hard to kind of tell the difference between that and just standard error. But with all this crazy Bayesian analysis,
And also depends on where on the curve it is, because the higher you get, the higher magnification there is. So even if there's a small planet up here, it's going to be bigger. So this is where you want to observe the most, and that's where you're going to get the small little planets. It's like if it's right at the top or somewhere near the top. And I believe this one was 1.5-ish Earth masses, if I remember. It was the smallest one before they discovered the new ones that everyone is like going crazy about.
What if there was, or how do you know it's like a fixed object and not like a binary stars?
So it, again, it's from the Bayesian analysis. It could be a binary star, but based off how the Bayesian analysis, the masses work out, and how you determine all this crazy parameter space. It's actually parameter space, and they get parameters for all these different things, and then wherever they cross, that's
so to put this in plain English, a lot of complex analysis.
Yeah, so technically you can observe binary stars this way.
But binary star would most likely have slightly bigger blips. It would probably be a little bit bigger than a planet. I would assume. Any more questions? All right.
No, I'm just saying that's really cool. That's awesome.
So if you want to be hooked up with anything gravitational lens-like, talk to me and Jake.
Yeah, and also I talked to Rob a few days ago, and he said there might be a possibility to continue this during the summer. So if any of you guys are going to be here during the summer, you can actually help with continuing this research, because he might be in New Mexico or France or Spain or somewhere. So he was like, I might need someone to help me with this. So there could be a possibility that we continue this during the summer if people are going to be here.